Welcome to the High Voltage AI Podcast. Today we're taking a deep dive into an issue truly reshaping the energy landscape. Why data center developers are sometimes buying substations even before they acquire the land. It sounds counterintuitive, but it's becoming the new normal. I mean, think about this example. Amazon Web Services, right? They planned this huge 1.2 gigawatt data center campus up in Northern Virginia, and they actually started by acquiring an existing 230 kilovolt substation and its crucial transmission rights. That electrical infrastructure alone was valued at, what, roughly $350 million? That's about $7 million per acre just for transmission access. This isn't just shrewd real estate speculation. It's a profound shift in how we build out our grid.
It absolutely is. And this deep dive is a key part of our special week-long series featured in the PXRD newsletter on Substack. We've designed this series specifically to help electric utility engineers, understand both overhead and underground construction types. We're building on what we've explored already this week. On Monday, we dove into the sheer data center tsunami and its massive impact on grid consumption. Then on Tuesday, we broke down how grid consumption is projected to jump from just 4% to a staggering 15% in only 6 years. And yesterday, Wednesday, we tackled the challenges of distribution design when a 50-megawatt load becomes, well, normal.
That's right. And for you, the listener, today our mission is to zoom in on the transmission level. We're looking at the planning bottlenecks and, frankly, the queue crises that arise when these massive individual loads aggregate into system-wide infrastructure challenges. We want to unpack why this isn't just the biggest challenge facing transmission engineers right now, but also perhaps their biggest opportunity. Ultimately, what does all this mean for the future of our electric grid?
Okay, let's unpack this. So what's truly astonishing here is the sheer volume of projects currently sitting in interconnection queues across North America. It's a staggering picture of the scale of this challenge. Okay, so let's talk scale. PJM, you're looking at over, 2,600 gigawatts in their queue, which is that's 5 times their current peak demand.
5 times, wow.
Yeah. In ERCOT, it's over 450 gigawatts in various stages. That's 3 times their current peak demand. And CAISO has over 350 gigawatts pending, about 2.5 times their peak demand. These numbers alone, they just highlight a grid under immense pressure.
Those numbers are incredible, but what's even more striking, I think, is how much of that is driven by one specific type of load. Because an estimated 30% to 40% of these queue requests in major markets are actually from data centers. And this isn't just theoretical, right? These aren't future projections from some economic model. These are formal requests from real customers with significant investments already on the line.
Precisely. This means even if only, say, 20% to 30% of these queued projects actually materialize, which honestly is a pretty conservative estimate, we're still looking at transmission system expansion requirements that simply exceed anything in the history of the electric grid. This is an unprecedented level of demand on our infrastructure. It demands a completely different approach to planning.
And here's where it gets really interesting and, frankly, a bit unsettling. The timeline reality. The average queue time from an interconnection request to actual energization is typically, 3 to 7 years?
Yeah, about that.
But data center developers who are building these facilities at breakneck speed often expect a much faster turnaround, usually within 18 to 24 months. The problem is, major transmission additions like building new lines or substations typically require 7 to 15 years for planning, environmental approval, and construction.
Which is just ages compared to what data centers need.
Exactly, a huge disconnect.
This creates a significant, almost impossible gap. We're looking at a 5 to 13-year disconnect between what these customers need and what's currently possible with our existing planning and construction processes. This isn't just an inconvenience. It's a huge driver for why we're seeing these radical proactive measures like the substation acquisition you mentioned earlier. The grid simply can't build fast enough under the old rules.
So where is this gap creating the most intense pressure right now? Let's dive into some of the regional transmission bottlenecks, starting with what I like to call the data center capital of the world. PJM, Northern Virginia, specifically Loudoun County, hosts over 25% of global data center capacity. It's North America's most acute transmission bottleneck, hands down.
And the constraints there are truly significant. I mean, the 500 kilovolt system operates at over 95% capacity during peak conditions. It's essentially maxed out. Their 230 kilovolt network has multiple circuits nearing thermal limits. Existing substations are at or near capacity. Plus, and this is a big one, there are very limited corridors for new transmission lines, which is a major hurdle for physical expansion in such a dense area.
So what does this all mean for the future infrastructure needed in this region? I mean, the projections are pretty eye-watering. For 2025 to 2030, PJM is projected to need 8 to 12 new 500 kilovolt transmission lines and 15-plus major substation additions or expansions.
That's right. We're talking an estimated total investment of $8 to $12 billion in transmission infrastructure just for that area. And the timeline challenge for environmental approval and construction alone is a daunting 10 to 15 years. It just shows the scale of the task.
So what are they doing? They can't just wait 15 years.
No, absolutely not. To address this, they're implementing some critical engineering solutions. These include grid-enhancing technologies like dynamic line ratings and power flow control devices. We'll get more into those later. They're also using high-cost underground transmission for those constrained corridors where overhead isn't feasible. Plus, converting existing 230 kilovolt lines to 500 kilovolt operation, essentially upgrading the highway, like you said, without physically building entirely new ones. And even series condensation to increase existing line capacity. It's a truly multi-pronged approach, trying to squeeze every last drop of capacity out of the existing system while also planning for the big new builds.
Okay, let's shift our focus south to ERCOT, the Texas data center boom. The Dallas-Fort Worth Metroplex is quickly becoming the second largest data center hub in North America.
Yes, and the system challenges in ERCOT are equally daunting, though maybe a bit different in flavor. They're projecting 150 gigawatts peak demand by 2030, up from 85 gigawatts currently. That's nearly double. You've got increasing renewable penetration, which requires more grid flexibility, multiple 345 kilovolt constraints right in the Dallas-Fort Worth region. Also, there's CREZ, that's Competitive Renewable Energy Zone infrastructure lines, built specifically to carry power from large-scale wind and solar farms, are now approaching capacity themselves.
What's fascinating here are the unique ERCOT factors that set it apart. It's a very different market structure. It's a market-driven environment that allows for merchant transmission development, meaning private companies can propose and build transmission projects, which is quite unique. Their competitive transmission planning process also creates unique opportunities for innovation. Plus, they have a different process for generator versus load interconnection. And, crucially, their islanded grid, not connected synchronously to the rest of the U.S., requires enhanced stability planning. That adds another layer of complexity.
It really does. It means they have to manage frequency and stability entirely within their own borders. Now, moving west to CAIS, Silicon Valley, we see different but equally challenging constraints. Bay Area data center development is heavily constrained by environmental and urban factors. There's limited transmission capacity getting power down to the South Bay via the Peninsula Corridor. It's a real bottleneck.
And the environmental restrictions are a really big deal there, aren't they?
Right.
We're talking about endangered species habitats and critical wetlands, which create massive hurdles for new construction. It's not just about finding space, it's about navigating incredibly complex regulations. Plus, with dense urban development, you have extremely high real estate costs and permit complexity that slows everything down significantly. Add to that enhanced seismic design requirements, which increase construction costs. Well, it makes for a very difficult environment for building new infrastructure at the speed and scale needed.
Absolutely. Which brings us to a critical point. The economics of transmission expansion, particularly the question of customer versus utility cost responsibility. This is a huge debate right now. Traditionally, transmission upgrades triggered by individual customers were often assigned directly to those customers. Network upgrade costs, participant funding. The customer basically advanced the construction costs.
Right. The causer pays principle, more or less. But the sheer scale of data center demands completely changes that traditional model. When a single customer triggers, say, $500 million plus in transmission upgrades, that old way of doing things becomes really problematic. Why? Because these upgrades often offer system benefits to multiple potential customers, not just the one who triggered it. They also drive significant regional economic development, making it a broader public good benefiting the entire community.
Exactly. And there's also the very real utility risk. I mean, what if a huge data center project doesn't materialize after the utility has already spent billions? Or if it gets significantly delayed? The utility could be left with stranded assets. Billions invested in infrastructure for a load that never appears, or appears much later. And if these massive costs are simply socialized across all customers, it can significantly impact everyone's electricity rates. So it's a real balancing act. You need fairness, but also pragmatism.
So how are utilities adapting? They must be developing innovative new cost allocation models, right?
They are. We're seeing hybrid approaches emerge. Things like shared investment, where the customer might pay, say, 50% to 70% of the upgrade costs and the rest is rate-based. There are also economic development rates designed to attract large loads but also recover costs fairly. Infrastructure banking is another idea, where the utility proactively pre-builds infrastructure in high-growth areas, anticipating the load. And even special-purpose entities, which are essentially giant ventures between utilities and developers for specific infrastructure projects.
Can you give us an example?
Yeah, a great example of this is Dominion Energy Virginia. They faced this head-on. They implemented a special data center rider tariff specifically for large data centers. This allowed them to invest $6 billion in transmission upgrades needed for this growth. The cost recovery comes through a mix of direct charges to those large data centers and some inclusion in the general rate base, reflecting the broader system benefits. And what's more, and critically important, they've worked hard to accelerate permitting and construction processes to try and meet the demand faster. It's a model for proactive investment and risk sharing.
Okay, let's talk about the system impact study challenges, because modeling these massive new loads concentrated in specific areas is incredibly complex. It's not like adding a few houses here and there.
Right.
Traditional studies generally assume, gradual load growth over 10 or 20 years.
Right. Nice, smooth curves.
It's exactly. Distributed load additions across the service territory, typical load characteristics, and standard N-1 contingency analysis. Just to remind listeners, N-1 means the system is designed to withstand the loss of any single major component, like a transmission line or a generator, without service interruption.
But data center studies require a completely different approach, a radical shift. They demand step change analysis for immediate full load operation, not gradual growth, but instant, massive demand the moment they flip the switch. You're dealing with concentrated loading from multiple large facilities, often clustered in small geographic areas. This necessitates enhanced reliability beyond N-1. We're increasingly talking about N-2 contingency analysis, meaning the system has to withstand two simultaneous major component failures. That's a much higher bar. It also requires complex dynamic studies for stability analysis during large load loss events, which can cause cascading failures if not properly managed. Losing a gigawatt instantly is a huge shock to the system.
And it doesn't stop there, does it? Protection system coordination becomes a huge challenge, too. How do these massive data center loads complicate the grid's existing protection systems, the relays and breakers that isolate faults?
Oh, significantly. Large data centers complicate protection by fundamentally changing fault current levels and direction. This can throw off existing distance protection settings. These are the automated systems that detect and isolate faults on lines. It also requires intricate time-current coordination between the utilities protection and the customer's own internal protection systems. They have to work together perfectly. And it demands enhanced communication across the entire grid to ensure everything works seamlessly during a disturbance. When you have a sudden massive load change or a fault near one, it changes the electrical landscape in ways that demand very precise and coordinated responses from the protection systems.
So what are utilities doing to address these complex protection issues? What are the solutions?
Well, they're implementing various advanced solutions. These include wide area protection schemes that look at the grid more holistically, not just locally. Adaptive protection is another key area. These are systems with settings that can actually change based on real-time system conditions, making them more flexible. Phasor measurement units, or PMUs, are crucial. They provide hyper-accurate, real-time monitoring of voltage and current phase angles across the grid, giving operators much better situational awareness. We're also seeing more centralized protection via remote control centers to manage this incredible complexity, making protection less localized and more system-wide.
Okay, so facing these challenges, the queues, the cost, the complexity, this is where grid-enhancing technologies truly become game changers, right? Helping us solve this puzzle without always resorting to massive new construction, or at least bridging the gap. Let's start with dynamic line ratings, or DLR. We typically rate transmission lines for worst-case weather conditions. Think high temperature, low wind, which limits their actual capacity most of the time. So what's the big difference with DLR?
Exactly. The insight here isn't just that DLR adds capacity, it's that it forces us to fundamentally rethink how we've always rated transmission lines. We're moving from static, worst-case assumptions to dynamic, real-time optimization. It's a smarter way to use what we already have. DLR can offer a 15% to 30% capacity increase under favorable or even just average conditions. It provides real-time hourly adjustments based on actual weather data, temperature, wind speed, solar radiation. This means we use the line for its true thermal capacity at that moment, not some conservative book value. This can actually defer expensive new line construction for years in some cases. And it provides enhanced capacity specifically for peak data center loads, which often coincide with times when DLR can offer more throughput. It's about truly optimizing existing infrastructure.
The implementation challenges, though, are real, aren't they? It sounds great, but it's not simple. You need comprehensive weather station networks along the lines, integration with energy management systems, new operating protocols for dealing with variable ratings. Operators need to trust it, and you need regulatory approval for these new dynamic methodologies. It's not as simple as just flipping a switch.
Definitely not trivial, but the payoff can be huge. Another crucial game changer is power flow control devices, specifically FACTS technology. That stands for Flexible AC Transmission Systems. These devices provide real-time power flow control, allowing grid operators to actively steer electricity where it's needed most, rather than just letting it follow the path of least resistance. Examples include static VAR compensators, or SVCs, for voltage support, thyristor-controlled series compensators, or TCSCs, for controlling power flow along specific lines, and unified power flow controllers, UPFCs, for comprehensive management of both voltage and power flow. All of these help optimize existing transmission corridors for data center loads by actively managing how power moves across the grid. It's like adding smart traffic signals to the electron highway.
And let's not forget grid-scale storage integration. Battery energy storage systems are no longer just for, say, smoothing out solar power. They're providing crucial transmission services now. What kind of impact are they having in this context?
They're incredibly versatile. Battery energy storage systems, or BESS, offer frequency regulation with sub-second response, providing vital grid stability, especially with large, potentially variable loads like data centers. They offer voltage support, which is critical for maintaining power quality near these demanding loads. They can provide congestion relief through strategic charging and discharging during peak loading periods, effectively acting as temporary transmission capacity upgrades. And they even offer enhanced black start capability for system restoration after widespread outage. They're really becoming a Swiss Army knife for grid operators facing these new challenges.
Okay, this massive influx of concentrated load also demands advanced planning methodologies. We touched on N-1 and N-2, but it goes deeper than that. Traditional planning seems inadequate. So what does probabilistic planning bring to the table?
Yeah, probabilistic planning is a fundamental shift away from purely deterministic criteria like N-1. It inherently involves analyzing multiple contingencies, including N-2 or even more complex scenarios involving common mode failures or cascading outages. Critically, it focuses on understanding the economic impact of data center outages. These facilities can have a value of lost load in the tens of millions of dollars per hour. So reliability isn't just about keeping the lights on, it's about preventing catastrophic economic losses. This leads to risk-based planning, which incorporates reliability economics. We use that value of lost load to calculate customer-specific outage costs, conduct detailed risk assessments using probability-weighted reliability metrics, perform investment optimization through rigorous cost-benefit analysis considering that risk, and use performance metrics specifically tailored for these critical large customers.
And because data center development has so much uncertainty, you're dealing with future tech, like AI growth, economic cycles, shifting demands. Scenario-based analysis is also crucial, right? You can't just plan for one future.
Exactly. It means utilities need to plan for multiple plausible future scenarios, not just a single forecast. You look at the base case, sure, but also high-growth scenarios considering the impacts of AI surges or other emerging technologies, and also economic sensitivity, what happens in a recession versus a boom cycle. So adaptive planning becomes key. This means designing infrastructure that can actually accommodate multiple scenarios flexibly. Think modular substations that are easily expandable if load growth exceeds expectations. Flexible routing options for transmission corridors that can handle different development patterns. Staged construction for phase development that matches load materialization so you're not overbuilding too early. And fundamentally preserving option values for future expansion. It's about building agility and resilience into the grid planning process itself.
We've seen these methodologies and technologies put into action. Let's look at some real-world case studies, starting back in Northern Virginia with their transmission solution. They faced that truly staggering problem, 2,000 megawatts of data center load growth in just a 5-year period. What did they do?
The solution was massive, a $4 billion transmission expansion program. It wasn't just one thing. Key elements included building 6 new 500 kilovolt transmission lines, constructing or expanding 12 major substations, deploying grid-enhancing technologies like DLR and potentially power flow controllers on existing lines to maximize their throughput, And crucially, as we mentioned with Dominion, implementing accelerated permitting and construction processes by working closely with regulators and stakeholders. The results really speak for themselves. Interconnection queue times in critical areas were reduced from 7 years down to about 3 years, which enabled something like $15 billion in private data center investment to move forward. It's created a powerful model, albeit expensive, for other regions grappling with similar rapid growth.
Okay, let's contrast that with Texas. ERCOT took a different path, more of a competitive market approach, to handle 3,000 megawatts of projected data center growth. Their solution was market-driven transmission development. What were the key elements that made this work, or at least aimed to make it work?
Well, the ERCOT approach leverages its market structure. Key elements included a truly competitive transmission planning process where multiple entities can propose solutions. Merchant transmission development rights, allowing private investment to build needed lines speculatively or under contract. Customer-funded upgrades, often with cost-sharing mechanisms to balance the burden. And importantly, smart integration with renewable energy development, trying to co-locate or share infrastructure where possible. What's truly innovative there, potentially, is how they've facilitated or are seeing the emergence of combined solar and data center facilities, shared transmission infrastructure, integration of battery storage alongside these loads, and optimized land use and permitting driven by market forces. It's a more decentralized, holistic approach, showing how a market-based system can try to drive innovation in grid development, though it has its own complexities and challenges, too.
So wrapping this all together, what does this mean for you, the transmission engineer, working on the front lines of this energy transformation? It feels like the ground is shifting beneath our feet.
It really is. The data center transmission challenge isn't just about building more infrastructure, though that's part of it. It's about fundamentally rethinking how we plan, approve, finance, and construct transmission systems. There are some key paradigm shifts happening that demand new ways of thinking. We're moving from planning for gradual load growth to planning for step change additions and immediate full load operation. That's a huge mental shift. Load growth is shifting from being nicely distributed across service territories to being highly concentrated in specific regions, overwhelming local systems. We're also moving from standard N-1 reliability criteria to premium reliability, needing to meet the 99.99% plus reliability needs of data centers where outages have multi-billion-dollar consequences. And finally, planning itself is shifting, or needs to shift, from being reactive waiting for confirmed load to being proactive, strategically pre-building infrastructure based on solid projections and scenario analysis.
So for transmission engineers listening right now, what are the immediate actions they can take or advocate for within their organizations?
Okay, some immediate actions. First, focus intensely on queue management. Develop fast-track processes. Improve study efficiency for these massive interconnection requests. Every month, saved matters. Second, aggressively investigate and implement grid enhancement technologies like dynamic line ratings, power flow control, and potentially topology optimization where applicable. Get more out of what you have. Third, develop multiple transmission expansion scenarios through robust scenario planning. Don't bet on just one future. Fourth, work closely with regulatory teams and stakeholders on new cost allocation methodologies. We need fair, efficient ways to fund these necessary upgrades. And finally, evaluate grid-scale storage and renewable integration, not just as generation resources, but as technologies that can provide essential transmission services while serving these massive data center loads. Think holistically.
Excellent points. And for tomorrow, we'll wrap up our Data Center Week by diving into the practical engineering solutions that are actually working in the field, with real-world case studies and lessons learned from specific projects.
Looking forward to it.
But for today, here's a final thought for you, our listener. What transmission bottlenecks is your specific region facing with data center development, or perhaps other large industrial loads? Have you seen successful examples, or maybe less successful ones, of accelerated transmission planning and construction in your area? The utilities, the engineers, the planners that solve this transmission puzzle are truly defining the next generation of grid infrastructure. It's a massive challenge, but also a huge opportunity to innovate.
Absolutely. Thank you for joining us for this deep dive into transmission planning, bottlenecks, and queue crises.
If you'd like to leave feedback or have any questions, feel free to reach out to me at alex.reed.power.podcast@gmail.com.
And you can reach me at emma.quinn.power.podcast@gmail.com. We'd love to hear your experiences.